Hello, I thought I'd try and make a video on how to go about debugging emulation issues with the MyC64 core using simulation tools. So I thought this could be interesting to people who might be interested in helping out but don't know how to get started. And well, yeah, I guess that's about it. So I recently debugged this issue that I found quite interesting. It was an EasyFlash cartridge for Maniac Mansion and McKracken, a combined cartridge for those two games that failed to load up on the core. And what happened was pretty much what we can see up here in so this Onslaught logo for the intro was shown, and then it crashed. Of course, that doesn't say too much unless you know what it's supposed to look like. So let's switch over to Vice and have a quick peek at what's supposed to happen. So loading up this cartridge. And there we go. That's the classic McKracken game. Um, so that's what it's supposed to look like. But what happened here was something different. So um, these, yeah, let's take it from the beginning. For simulation of the core, we have this tool called Core Top Sim. Pretty stupid name, yes, but it's actually quite useful. So this thing is a yeah, it uses Verilator to perform RTL simulation of the core, and it allows us uh, to extract various traces, either of all signals inside the RTL or program instruction traces from the 6502 CPUs and IEC traces from the serial bus. It allows us to extract video frames, to simply dump them to PNG files. We can inject keyboard sequences to make so to make stuff happen basically. And of course we can load PRG files. We can mount G64 files, and then you would need a key sequence for load and run and all that. And you can load up CRT files as well. So what we did here was simply run it like this. We say please dump video. That will produce a PNG file for each video frame. So for each vsync pulse, we save the so the simulator captures the video output signals, and when there is a vsync signal, it saves it to PNG and increments the counter. And here we say please load up the cartridge for the EasyFlash cartridge for McKracken and Maniac Mansion. So if we run that, which I did previously, then we end up with this, about 500 PNG files. And about here is when the cartridge is inserted and screen goes blank, and then after a while the Onslaught logo appears. So this is, take note here, this is video frame 498. And then in video frame 499, it looks like it's already crashing. So there appears to be some issue here. There's supposed to be a tentacle jumping around and some scrolling text, as we saw in device run just a few minutes ago. So how do we go about debugging this? And this is an exercise I did very recently. So yeah, that's why I thought it was a good idea to try to record it, because it was actually quite interesting. So the video frame was 498. All right. So let's rerun this, but also extract a CPU instruction trace. So we say minus CPU C64, the C64 CPU trace, and we want to extract that into CPU or C64 CPU trace.txt, like so. And since we know it was video frame 498, we might also be interested in extracting a full signal trace, so we can have a look at what's going on inside the design. So we add that as well, and that would be minus trace dump.fst. So we want to extract signal trace in FST format, and this significantly slows down simulation. If you extract, you can either pick certain modules in the hierarchy that you want to trace. That would speed up tracing. Or you can also simply just delay enabling of tracing until we approach the point where the interesting event will happen. And since we saw things went wrong at video frame 498, let's begin tracing at video frame 495. So minus trace begin frame 495. And then I'll run this. And this will take a few minutes, not too long, but I might pause the recording here. So what's happening right now is that all these printouts moving past the screen, that's the EasyFlash cartridge being downloaded from a mock-up of the Analog Pocket framework. So the file size is about 900 kilobytes, I believe. So we downloaded about half of it now. And once that has finished, the core will be reset and execution will start from the cartridge by normal means. I think I'll pause the recording here and get back once we reached video frame 500, I believe. That would be a good stopping point. All right, so about 2-3 minutes later, we have reached video frame 501. And well, let's just have a look at them again and see. Oops, it's the other way around. And see where we are. So scrolling to the end. We still see 498 being messed up. Yes, more 499 gets messed up. So now we extracted a CPU trace, so we can have a look at that. And the name of that is C64 CPU trace.txt. So this contains basically a, I don't know what to call it, a disassembly trace. So the leftmost column is the address where the instruction is fetched from. The following column is the bytes making up the instruction, then the mnemonic of the instruction, register contents before the instruction executes, and then we have some information here to allow us to correlate with the frame dumps. So F0 means this corresponds to video frame 0, and then C is the cycle or simulation time actually in picoseconds currently. Anyway, so we said interesting stuff happened at 498, so let's go to frame 498. So search for F:498. That should do it. Takes a short while, and now we arrive here. Okay. Now, of course, debugging this stuff is, well, I guess you end up staring at this for a while, swearing at it, and hopefully you find something interesting. I had a look at this for a while, and then I noted something. I mean, you look at the proximity of the frame where things appear to go wrong. So it's not, you have some clue at least. So I spent some time looking at this, and I noted something that looked weird. And I'll just search for that now. There was this. As you can see, this is still video frame 498. We see this long sequence of NOPs. Maybe that's not so weird, but then it appears that the disassembly fails for several instructions that follow. So without knowing anything, that seems like a good place to start. So what's going on here? This is video frame 498, and well, yeah, we need to know a little bit about these registers. So let me grab a browser. Then we can have a look at the C64 memory map, and we can see here that it's loading something from D012. Then it's clearing the carry bit, and it does an add with carry, adding immediate 2 to that value, and then it stores it back into D012. So what is D012 then? Well, D012 is a register inside the VIC. And if you read it, you get the current raster line bits. And if you write it, then you set the line on which to generate an interrupt when that line is reached. So the raster line is basically the y coordinate of the screen. So it adds 2 to that, and then it does some stuff, and it does a clear interrupt. So clear interrupt disable bit. So we can see here the I is set here. So that means interrupt disable bit is set. So interrupts are disabled when we're here. Then it clears that flag. So now interrupts are enabled. And then there's a long sequence of NOPs at consecutive addresses, 20, 21, 22, 23, 24, etc. So all 1 byte instructions. And then for some reason we reach a RTI, return from interrupt. And apparently what so RTI will will pop the return address from the stack, I believe, and then we jump there. And when it does, it starts executing garbage. It appears, at least. So that's interesting. What I did next was to, okay, does this happen? What happens in Vice? Does Vice ever reach 433F, for instance? Does it reach 4321? Well, let's find out. Let's begin with the first one, 4321. So we start it up, press Alt H to bring up the Vice monitor. Then we say we want a breakpoint at 4321. Was that the address? 4321, yes, exactly. And then we continue. And indeed, that breakpoint is reached. Now we can just disassemble a bit, and we see there are a bunch of knobs. Looks pretty much the same, and indeed there is also an RTI at the end. So interesting. Let's single step for a while and see what happens. So knob, 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 knob. And then apparently we take an interrupt because the interrupt disable bit is set by the CPU and it's jumping to the interrupt vector. Where the interrupt handler is. Okay, so it didn't reach the RTI instruction here. Does it ever reach the RTI instruction or the one just before it? That was for free F. Double checking here. For free F. So I delete all breakpoints. Break for free F. Then I just I just continue here. No, it doesn't reach that instruction. So it appears to take an interrupt while executing this long NOP sequence. So what's going on here? Well, I'm no demo coder and I don't really know that much about 6502 assembly and or C64 programs in general. But I think what's going on here is that you're trying to synchronize the CPU with the horizontal position of the raster beam. So the idea here would be that basically you're okay. So what is the current raster line? Then I set up an interrupt to happen not at the next raster line, but at the raster line after that. So we add 2. So that happens here. But interrupts are still disabled. The I flag is set. Then we enable interrupts and we we expect an interrupt to happen. And the reason for having NOPs here is to get the predictable. Each NOP takes 2 cycles to execute. So let's say we instead had a while loop or a branch to self loop or some kind of loop. Depending on what instruction you're in that loop, it will take varying number of cycles for the interrupt to take effect because an instruction can't be interrupted. You have to, the interrupt happens between instruction at the instruction boundaries. So I believe that is the reason for having the knobs, so that you somehow can calculate exactly how many cycles it will take from the point where you get the interrupt. The interrupt will happen at most 2 cycles. There will be at most a 2 cycle delay if the interrupt happens in this NOP sequence. And then you can probably calculate add up all the cycle numbers for the instructions in the interrupt handler to know exactly what horizontal raster beam position you have when you reach your handler code that is going to do something with that is going to need that. So that is what I think is happening here. And if you look at the execution time, so if we can for instance go here to mass work, I think There's an instruction set here. You can see that like store instructions, for instance, if the address is absolute, that would be a this would be an example of an absolute address. Then it consumes 3 bytes and it takes 4 cycles to execute. Then, for instance, we have an inc instruction here. Okay, so what about inc then? And again, we see if it's absolute address, 3 bytes, 6 cycles to execute, etc. And also of interest is the NOP. The NOP is 1 byte and it takes 2 cycles to execute. So if you sum up the instruction latencies, starting with this load here, then you end up with, and to this point here, then you end up with, I think, 100 CPU cycles. And as we know, the pixel clock is running at 8 times that speed. The pixel clock is 8 megahertz, the CPU clock is 1 megahertz. So that means that we will have covered 800 pixels in this time. So that's, I'm not sure if it's two complete raster lines, or if it's, but it's definitely a lot more than one. 1.5 to 2, I would say. I could of course check that, but never mind. So, all right. So the idea is that the interrupt should hit somewhere when we are inside the NOP sequence. By the design of the VIC and the C64 and all that, it's for certain the interrupt should hit while in the NOP sequence. The RTI should never be reached. I think that's the idea. And since we reached this point in my core, that's probably a bug. But how do we find out what's going wrong? Well, now we can have a look at the signal trace as well. And here we see, to correlate where in the signal trace to look, here we have the timestamp in picoseconds to look inside the signal trace. So let's bring up the signal trace here. GTK wave. Dump.fsd, like so. Excuse me. So yeah, now it makes most sense to bring this to a new workspace, like so, and then we also want to look at this at the same time. So, and I think it makes more sense to look at it like this. So let's see. How do we do this? So basically, we want to start looking. Yeah. Let's pick a signal. Let's pick a timestamp some slightly before our point of interest. So not that much before, but let's pick this one. Now, this is a bit clumsy, but it works. We can basically say that we want to begin our trace from this point, PS, for picoseconds, and enter. Now I hope that took effect. I'm not sure. Anyway, we can go inside the hierarchy and find the C64 and have a look at the CPU. the CPU, and the CPU has something called a sync signal, and that signal pulses each time it starts execution of a new instruction, or it loads, or the addresses it presents on the address bus is that of a new instruction. So it's very useful to look at. And then we look at the address here. And so if we look here, what's the address then? 4164. Here we have a sync pulse, and the address the address we see is 4164. Then we jump to the next sync pulse, and that is 4167, and that corresponds here. Then we come back to 4164, it seems. Yes. But now FF48. So we're here. So yeah, it looks like we are at the right place. We can move forward a little bit to here maybe, 4307, 4307. Now we're here. Here we're adding the 2. Okay, so what's going on with the VIC signals and the raster? What is the raster line when we are here? So the raster line at this point is E8. Okay, E8. And that corresponds here with what the accumulator ends up having after the load from this. So that looks good. Then we perform an add of 2 to E8, and then we end up with 90. And that is what we store back to. And what we store back to this register. And when we store to it, then it ends up in the raster IRQ register internally. So here we can drop a named marker here at 4307, and then we see here that okay, so now we store back 90. Yeah, okay, cool. So, but do we get any interrupt then? We should get an interrupt when we should get an interrupt when raster this register changes value to 90, which it will do, which it does here exactly. So we should get an interrupt pretty much immediately after this point, but we do not. Or maybe we do, I don't know, but it's not happening during the NOP sequence at least. And when we are here, what address are we executing then? Well, then we are at address 4337. 4337. 4337. Okay, but that's here. So we're still inside the NOP sequence. So if the interrupt actually happened here when it should, we should still be fine. Because we're still inside the NOP sequence, we haven't fallen off it yet, and well, but it doesn't appear to happen. Okay, so what are the interrupt signals here? We have an output IRQ signal. Okay, so there's no activity here. Interesting. We had some activity here, but then it died out, or didn't die out, but so we can actually look at that as well. So this corresponds to 4319, 4319. So what's happening there then? Well, it's doing an inc of D1, D019, D019. What is that? D019 is the interrupt status register. If you read the bits, and if you write the bits, it's acknowledge of those. So doing an inc of that will, yeah, I'm not sure. You read, but then you increment, and then you write. Yeah, anyway, it looks like it's clearing the interrupt. So that's what clearing the interrupt, and then after that we enable interrupts in the processor, and then we enter the NOP sequence. And as we can also see here, the NOP sequence is very regular in the pacing of sync signals. Here earlier it's more spread out because they take different number of cycles to execute those other instructions, but NOPs are very regular. And all right, so what else do we have here? We have, and of course, when you do this, you need to look at the source code of the VIC implementation to know what signals to look at. But I know that already somewhat, so I'll, or you can of course just, I mean, if you search for IRQ here, then you get stuff that's IRQ related. So okay, what can this be? 4 bits? That's probably the interrupt enable bits or something. Or it's pending bits maybe. Yeah, it's maybe pending bits. Yeah, it's probably pending bits to be honest. The interrupt enables are in RD1, as we said. Or maybe not. Now I'm confused. Let's have a look at the source code of the VIC implementation, just to orientate ourselves quickly. So core MyC64 RTL VIC. So what kind of IRQ stuff do we have here? Output IRQ is the output of the output of the module, obviously. So this guy will right. Yeah, so now we see here. So this is basically if logical AND of bits in IRQ and the D1, D01A register. D01A, what is that? D01A, that's the interrupt control register where you set the enable bits. So we expect to have raster interrupt enabled, and yeah, we expect to see this 0 bit of IRQ register of this IRQ register to be set when the raster interrupt occurs, and then that will that this reduction any or reduction or will pulse the or enable the assert the output IRQ signal. You can also look here raster IRQ. So it's so here we basically so raster IRQ. So with 8 megahertz clock, if cycle equals 0 and the current raster line is the same as the raster IRQ line, then we simply set the bit in the IRQ register, bit 0 in IRQ register, and as we just saw, then if it's enabled in the 1A register, that should generate an interrupt going out. So we see here the D01A register is the 0th bit of that is set. So but the 0th bit of the IRQ register is not set. Does it get set? Yeah, it does get set, but it doesn't get set until the very end, or yeah, it looks like the very end of the raster line. So that's weird. That's not how it's supposed to work. It should be. We can actually check that as well if we go to the what's it called, raster interrupt. It says so somewhere. Hmm. Yeah, I know I read this earlier, so it says something. Yeah, here we have it. Vic interrupts. Reaching a certain raster line. The line is specified by writing to register D012 and bit 7 of D011. The test for reaching the interrupt raster line is done in cycle 0 of every line for line 0 in cycle 1. Okay, so it looks about right. It should be cycle 0, but maybe our cycle is slightly off compared to what it should be. Maybe it's, yeah, since obviously there could be just about any bugs in this implementation. But if we, what value does cycle have at this point? Well, let's have a look. Cycle. And let's zoom in a bit. We should zoom in here because this is where we are interested in what's going on. We're interested in why it's not happening here. Okay, so cycle 0 here. Yeah, but then it's not, it doesn't get incremented until cycle 1. Okay, that's interesting. So how does actually raster, or maybe it's called Y inside here? Let's have a look. Do we check cycle 0 for incrementing that? That seems wrong. So I to get around this, we could do two things. Either we could change this cycle to be 1 here and see what happens, or it seems that this should increment one step earlier, maybe at cycle 3F and not in cycle 0. Or I mean, we shouldn't check for cycle 0. We should check for cycle 3F because then it would, when we reach cycle 0, or it would coincide with the new value will be already at cycle 0 then. So that should also work. But we can just let's change this to 1. All right, saved. Now let's go back and rebuild the simulator like so. Build sim sh. This takes a few minutes or 1 minute maybe. I can keep babbling in the meantime. So yeah, so if we change that, then we should get an interrupt here, and then in theory that interrupt should happen at yeah, here we are at cycle address 4337, so that interrupt should happen here and before we run out of knobs or run out the knob sequence ends. So let's hope for that. Now it's doing the final link step, I believe, which is a bit time consuming. No, now it's doing the link, but it will be done shortly. Not so shortly, maybe. Yeah, no, now it's done. All right. So now we can, let's just rerun the last command. Yeah, let's just rerun exactly what we did before. And I'll pause the video and go take a glass of water. All right, now we have reached video frame 501 once again. And well, so what happened this time? We can have the simulation running while we have a look at the results. So here, looking at the video frame dumps, 498. You can zoom in a bit in case it gets too small in the video. 499 looks okay. 500 looks okay. Oh, and now there's some actually text. And then, yeah, I believe those are from a previous simulation run where it crashed, those blue screens. So, yeah, I should have deleted them. Okay, but it looks like it's working much better. So now let's stop the simulation. Now let's have a look at the CPU instruction trace, reloading the file. What happened here? Ah, now it woke up. All right, good. Yeah, so here we are once again doing the same thing, reading the raster line from D012, adding, incrementing with 2 and writing it back. And then we begin the NOP sequence, and this time we see pretty much as we said, well, almost as we said. The interrupt occurs around 4337 this time, and we don't reach the RTI and we don't run out of the knobs, and we don't get undecodable instructions afterwards. So that looks like an improvement. How does it look in the signal trace then? What happens here? So previously we yeah, output IRQ was here, and here is this guy is the intermediate interrupt bit. So this one should now change to 3 here instead of here. Let's reload. I haven't reloaded the signal trace here. It's a click reload. Now it looks like this. All right. Now it looks like this. Okay. Now I'm a little bit confused. Now we get now we now we get the interrupt already at 8F. One cycle is 1. Okay. And this happens because raster IRQ is still 8F at this point. Yeah. Now I'm rather confused. What the hell happened here? happened here? Oh, okay. Maybe we are shifted a bit. So it's not, now we see here that this guy here reads, the value read from D012 is now 8D. Then it increments by 2 and we end up with 8F, and that's what we write back. And the knob sequence is here. So it appears that we ended up being shifted up a few raster lines. Didn't see that thing coming, but maybe that's a reasonable consequence of the changes we made. Anyway, we see here at now the interrupt gets set here because now the comparison 8F and cycle is where is cycle here? Cycle is 2 and there was cycle 1. And this is where the interrupts get set, or a consequence thereof. So yeah, so that's where the raster and raster-IQ matches, and that's corresponding to fetching an instruction at address 4337, 4337, 4337, 4337. Yeah, that looks reasonable. That looks pretty reasonable. Then the interrupt gets set, and we begin fetching the next instruction. Then it reaches the CPU, and then the CPU acts on it, and the output looked better. So this could be a reasonable fix. In reality, though, it's pretty stupid to run sophisticated games and see where they break and then try to fix it. It would be time would be much better spent running VIC2 test suits from device emulator test benches, and then fixing stuff there, because then it would be more isolated, and this is like yeah, not a very efficient way to hunt down issues. Anyhow, let's disable all the tracing and have the simulator running freely for a while and see if we can actually get the game booted up. So I'll do that. So let's go here, and yeah, we can kill that guy, and remove all the PNG files, and then now we want to run the simulator again, but we don't want any time-consuming signal trace, and we do not want a CPU trace either. So let's just run this and let it run for a few minutes. So I will again pause the video. And now I'm back. It took a few minutes to run the simulation, producing about 1800 video frames. Initially I made a mistake because I realized I also need to add a minus keys to inject a space bar press at video frame 525, because if we look here at our video frames, recorded video frames, yeah, basically somewhere around here you need to press spacebar to end the intro, otherwise it just gets stuck there. So yeah, the best way to Now we have so many frames. So the best way to view these is actually to produce a small MPEG out of them with the FFmpeg, like so. Now we can produce a Maniac Mansion.mp4 that we can. Yes, I did this previously, so I just overwrite it. And then VLC. And here we go. The Onslaught intro doesn't look quite right, but it doesn't crash at least. Then some selection, Zach McKracken or Maniac Mansion, and Lucasfilm Games. And yeah, Zach McKracken loads up. So that's pretty cool. It looks like that game might actually work. This is all in simulation, of course, because I haven't yet added EasyFlash support for the yeah, I need to use external memory for that to work, and I haven't yet done so. So far only simulation, but this is a very good good sign at least. Yeah, I think that concludes this video. So I want to show demonstrate how to use the simulation tools and how to go about debugging emulation issues, and I hope I managed to do that to some extent. It's rather unpolished video, but if someone is interested, then I think it can be useful. Otherwise, I wouldn't really recommend watching it. It's mostly me rambling. Well, till next time, thanks.